Okay, welcome Chem 110. This is week 2 assignment. You'll just have to ignore my voice. I am sick. Unfortunately, that's what happens when you get busy in the semester. But I'm going to do an example of each of these questions of the main component of this assignment for you so you have an idea of what I'm looking for. I have a periodic table right here to guide me. So you need one in front of you too anytime you do one of these assignments because that is basically our foundation for all of these problems. That's where you're going to get your answers. Okay, so let's look at part 1 up at the top. It says it's from reading section 2.3. So this is chapter 2, section 3 of the OpenStax book online. So let's look at the first question. So it says give the number of protons, neutrons, and electrons for the following. And we are going to do that. I'll do it for B. Okay, so the first thing that you want to do is locate where that element is on the periodic table. And what I'm going to do is I'm just going to increase the size of this so we can see it more easily. Okay, I think that's good enough. And then I'm going to circle what we're looking at. So here's carbon right here. C has a number 6 right here. That's the atomic number. C is the atomic symbol. And down here is the atomic mass. So when it asks for the number of protons, what that's asking for is that number right here at the top. So the number of protons is equal to 6. The number of neutrons for C18 is taken first from this number. This is the mass number, and you subtract the number of protons from that. So 18 minus 6 gives you the number of neutrons, which will be 12. Okay, and then next, that's the answer for neutrons. And then next is the number of electrons. So remember, if something is not charged, so if it is neutral, then the number of protons and the number of electrons are equal. So the number of electrons will be equal to 6 in this case because it is neutrally charged. Okay, so let's minimize this and scroll up here. I want to look at number 2 just so we are on the same basis of what is in an atom. Okay, so it says what is contained in the nucleus of an atom. The nucleus of an atom always contains protons and almost always neutrons. There are exceptions to that. At least one major exception is hydrogen. Hydrogen does not have any neutrons, but what I'm looking for here is that you understand the difference between electrons, protons, and neutrons. Protons and neutrons are contained in the nucleus. So right here I'm going to put protons and neutrons. Okay, let's skip to number 5. So number 5 says, what method is used to determine natural abundance of isotopes? This is taken directly from your reading. There's a method that's used to determine what the natural abundance of isotopes is. So again, I'm looking for a method, not a calculation necessarily, but what type of scientific method is used or tool is used to determine natural abundance. Okay, let's skip down to part 2. This is from reading section 7.1 to 7.3. So I'm going to pull that up in front of me so I can look at that at the same time. So 7.1 is ionic bonding, 7.2 is covalent, and 7.3 is Lewis symbols and structures. So 7.3 is going to be the most applicable to these few problems. So the first one asks or states, draw the Lewis symbol for, and let's look at calcium. So I'm still going to have the periodic table in front of me, and I'm going to blow it up a little bit. And when I'm looking at a Lewis symbol, what I'm first going to do is just write the atomic symbol for that element. So in this case, calcium is already written for you, but I'm going to rewrite that here. So calcium, Ca is the atomic symbol for calcium. And then I want to note the number of valence electrons. So for main group elements, and that's these elements right here and right here, these are labeled group 1A, group 2A, 3A, 4A, 5A, 6A, 7A, and 8A. A just means that it's main group. These are called transition elements, and these are also types of transition elements here at the bottom. So I'm only going to be asking you to draw Lewis symbols for main group elements, so that's the ones that are labeled A. And the number of valence electrons is equivalent to the group number that it is. So if I identify that calcium is in 2A, that means it has 2 valence electrons. So how I'm going to draw that is by drawing one dot and a second dot. Now, the dots don't need to start, I don't need to put one dot necessarily on the top and one on the side. I could have started at the bottom and then put a dot here on the left-hand side. But the general idea is that you are first going to write the symbol, and then you're going to look at it as if it's a box, and on every side of the box can contain 2 electrons for a total of 2, 4, 6, and 8. Now when I'm filling those in, I'm going to individually draw the electrons before they pair. So a wrong answer would be this. I would not put that for calcium because I want to individually put the electrons on the sides before they end up pairing. So since calcium only has 2 valence electrons, that would be your final answer. All right, let's skip on down to number 2 for part 2, and then asked to draw the Lewis structure. This is still related to section 7.3 of your textbook. I'm going to look at letter C right here. So we're going to look at H2O, which is water, and I'm going to draw the Lewis structure for that. So I'm still going to use the information that I did on the previous question by determining the number of valence electrons that water has, so altogether. So that means I need to know the number of valence electrons that hydrogen has, and I need to know the number of valence electrons that oxygen has. So hydrogen, being in the first column, has 1 valence electron, and there are 2 hydrogens in the water molecule, so that gives me a total of 2, I'm going to abbreviate this, VE, valence electrons. And then oxygen, being in group 6A, this is group 6A, that means it has 6 valence electrons. So that means I have a total of 8 valence electrons ready to be used to draw this structure. So in order to build the structure, the first thing that I need to do is to determine what is going to go in the middle, so what's going to be my central atom. So a good rule of thumb to use is the atom that is the most unique in the structure, in the molecule, is going to go in the center. So in this case, oxygen, there's only 1 of them, and there are 2 hydrogens. So that means oxygen will go in the center, and the hydrogens will go on the outside of the oxygens. After this, what I'm going to do is I'm going to draw a line which represents a bond between the external atoms, which are the hydrogens, to the oxygen, which is in the center. Now, what you have to remember in this case is that each line, since it represents a bond, represents 2 electrons. Each of these lines represents 2. So what I'm going to do with this 8 right here is that I'm going to subtract 4 total electrons, saying it's basically like a checkbook, or balancing your checking account, saying I had $8 to start with and now I just used 4, so I have $4 left to use. So if you remember from your reading, hydrogen only ever wants 1 bond, okay? But most of the other elements would like 8 electrons around them. In this case, hydrogen only has 2 around them, and if you look at oxygen, oxygen has 2, 4, has a total of 4. So oxygen is missing 4 electrons from getting to the goal. The goal is 8 electrons, okay, around most atoms. In this case, hydrogen is an exception, but almost all atoms would like to get to an octet, which means it has 8 electrons in its outer shell. Okay, so what I'm going to do, since I have 4 leftovers, I'm going to put 2 at the top and 2 at the bottom. So that would give me an acceptable Lewis structure for water, because oxygen has a total of, I'm going to count them, 2, 4, 6, 8 electrons around it. Hydrogen has 2 and 2 on each side. And at this point, and this was a little bit of an error here, I didn't show you that I've subtracted 4 from the 2 at the top of the oxygen and the 2 at the bottom. So I have a total of 0 electrons remaining. At the very end of drawing the Lewis structure, you should have 0 electrons remaining. You shouldn't have any more than 0, and you can't overdraw. You can't use more electrons than are available to you at the start. So your final, you should have used all of your electrons, all of your atoms with very few exceptions, one of them being hydrogen. All of your atoms should have an octet around them, and only use double bonds when absolutely necessary. So because I think that A is actually a little trickier, I'm also going to do A for you. Okay, so let's look at A. We have CO2. So remember, the first thing I need to do is add up the number of valence electrons. Let's look at carbon. Carbon is in group 4A, which means it has 4 valence electrons. Oxygen is in group 6A, which means each oxygen has 6 since there are 2 of them. That gives me a total of 12. So altogether, I have 16 valence electrons. Okay, using that same rule of thumb, carbon would be my central atom because it is the most unique atom. There's only one carbon and there are 2 oxygens. So I'm going to put oxygens on the outside, and then I'm going to single bond everything to the center. So that means I've used 4 electrons when I put 2 bonds. Okay, since I don't have any hydrogens here, I don't have an exception with the octet rule or with having 8 total electrons. And so what I'm going to do is I'm going to take the 12 I have left over, and in groups of 2, so in pairs, I'm going to add them to the outside, 2 electrons, then 4 electrons, then 6 electrons, then 8, then 10, then 12. I only had 12 to use, so I have 0 electrons left over. Okay, now I'm going to count to see that everything has an octet. So oxygen has 2, 4, 6, 8. I'm going to change this little pin so it makes a little bit more sense here. And this has 2, 4, 6, 8. But notice carbon only has 2, 4 electrons around them. So what you're going to do is you're going to take the electrons that are on the outside right here, and you're just going to move them. And they're going to make a new bond. So your new structure is going to look like this. A double bond just means 2 lines between the oxygen and the carbon. And now, instead of oxygen holding on like a greedy little oxygen to all of its electrons, it's going to share them with the carbon so that carbon can share in the joy of having 8 electrons. So oxygen has 2, 4, 6, 8. Carbon has 2, 4, 6, 8. And the last oxygen has 2, 4, 6, 8. So this would be an acceptable structure for CO2. Okay, so we're going to look at part 3. This is from the YouTube video and from your reading. So actually, if you go to 7.6 is the best part to read about Vesper theory. And you'll see at the very top of Vesper, or of 7.6, it says Vesper theory means valence shell electron pair repulsion theory. Okay, so you can write that down yourself, but I'm going to choose just, let's say, one of these. I'll choose A for us to do together. Okay, so this is NH3, which is ammonia. You want a periodic table and a Vesper geometry chart. I took one off the internet. All I do is Google in Vesper chart, and this is the one that I usually use for my classes right here. But this is the same that's in your textbook, so whatever format you like the best, it's up to you. Okay, so first step in determining electron domain geometry, which I'm going to give you a synonym for this. This is what's used in the YouTube video, electron domain geometry. This is the same on my chart as basic, okay, basic geometry. And when you see molecular geometry, this is the same as Vesper. These are synonyms. Okay, on a quiz or exam, I would use both sets of terms so that you only really need to be familiar with either electron domain geometry or basic geometry. I'll put both of them for you so that you won't be confused. But they're used interchangeably. Okay, so the first thing you need to do is draw the Lewis structure. I'm just going to do that for you really quick. So the Lewis structure for NH3 would look like this. There's a total of 8 valence electrons for NH3. 2, 4, 6, 8. Okay, So the focus on determining geometry is by looking at your central atom, the one in the very center. So all the questions that I'm going to be asking you are based off that. Okay, so after that point, you don't really need the periodic table anymore. So I'm going to move, oops, I guess I can't really move it because it's attached. I'm going to move this one in front of it. So my Vesper chart. Okay, the first question that you ask yourself when you're determining what the basic geometry is, let's call this question A. How many electron regions? And remember, this is all based off the central atom. So you look at the central atom, and you say how many electron regions are around it. Well, there's one here, there's another region here, another region, and another region, a total of 4 regions. What you're looking for essentially is either a bond, which is a line, or multiple bonds, or lone pairs of electrons. So these are all bonds, these 3, so these each count as a region, and this is a lone pair, which is another region, so I have a total of 4. So the answer would be 4. Okay, that's going to give you your basic geometry. So notice these numbers in this column right here, which you're going to identify as the number of electron regions right here. So number 4, that tells you that the basic geometry, notice it says basic geometry up top, basic geometry is tetrahedral. So your answer for the basic would be tetrahedral. Okay, the second question for Vesper geometry is how many are non-bonding? Another term for that is lone pairs. Lone pairs mean they're not bonding. They're all alone, they're sad. Okay, they haven't bonded with anybody. Or maybe they're not sad. Maybe they want to be alone. But whatever. They're not bonding. So how many of those 4 regions are not bonding? Well, notice there's only one. Just this region right here is not bonding. So what I'm going to do is right now, or just previously, I determined that the basic geometry is tetrahedral. Notice up here, these columns correspond to lone pairs. So since my answer was 1, I'm going to just move one column over, and that tells me my molecular or Vesper geometry is trigonal pyramid. So my answer is trigonal pyramid. So it's pretty simple when you get the hang of it. So, but remember first to draw the Lewis structure, and then after that, you'll ask how many electron regions are around the central atom, and then how many of those are lone pairs or non-bonding. Okay, good luck. Let me know if you have any questions.